Okay, so before we start problem 3, I need to discuss a few more key concepts that we're going to need in order to solve these problems. Now you noticed I erased the other key concepts, so if you didn't get those, you can go back and write them down. But I'm going to move on to these next ones. So I didn't get to cover the relationship here, but there's Ka, there's Kb, and there's Kw. And each of these are ionization equilibrium constants, and they're related to acids and bases. And they're related to each other. So first of all, let's talk about Ka. Ka is the acid ionization equilibrium constant. And it is calculated according to, well, first of all, let's write a generic equation for acids. Remember that we said acids are being represented as HA, and when they dissociate, they form H plus and A minus. HA is the acid, and we've already seen this before, right, in problems 1 and 2. And H plus is the number of protons, which we use to calculate pH. And A minus is the conjugate base. So those are our key players. Ka is calculated by taking the products, the concentration of the products, over the concentration of reactants. And so that's what we want to keep in mind. Next, and I'm going to move to black maybe, because that might be easier to see. You can imagine Kb is calculated similarly. So Kb is equal to the base ionization equilibrium constant get that out. So we have an equation for acids. The equation for bases has to do with OH. So we start with our conjugate base, A minus, our anion, and we add in water, which then gives us a conjugate acid now, HA plus OH minus. So instead of just taking just the acid and breaking it up into the H plus and the A minus, we first start with the conjugate base, which is the anion minus A minus, plus water to give HA and OH. It's going to make a little bit more sense in a second, okay? But just stay with me. All right, so if we're writing the we're writing the KB, and I wanted to write in here, this is base, and also could be represented, say it's conjugate base, and then this is conjugate acid. So this is the acid version, where we take the acid to form a conjugate base. We take a base, which is just an anion, add water to form the conjugate acid, and then we have this OH that's left over. And the OH minus is the concentration that's going to contribute to calculating the POH, which we just talked about in a couple of videos ago. So Kb, once again, products, HA times OH minus over A, the anion, and then we know that water is a pure substance, we don't include it. So that's how we calculate Kb. Okay, so now since we have these two relationships, let's circle them so that we can remember. Now, what about Kw? Glad you asked. So Kw comes in, which is equal to Ka times Kb. So that's similar to an equilibrium constant where we had different equilibrium constants to represent different steps, and then we multiplied them together that equal the total equilibrium constant. Here for acids and bases, the Ka times the Kb is equal to Kw, and we know that Kw is always 1.0 times 10 to the minus 14. That's going to always be true. So why does this make sense? Well, let's put this in for this. So if we put in H plus times A minus all over HA, that represents our Ka. And then we multiply by Kb, which is HA times OH minus gives, or over A minus, right? And that's supposed to be equal to Kw. Okay. Oh, and this is Kb. Now, we remember from a video or so ago that Kw also equals H plus times OH minus. And we're going to see that that is indeed still true for this example. We see that the anions go away and the acids go away. And we are then left with H plus times OH minus to be equal to Kw. Okay, so now we have all this, and we're going to go on and calculate problem 3.